Disjoint paths in directed and undirected graphs. In section 7.1, we described a flow F as a kind of traffic in the network, but our actual definition of a flow has a much more static feel to it. For each edge E, we simply specify a number f of E saying the amount of flow crossing E. Let's see if we can revive the more dynamic traffic-oriented picture a bit and try formalizing the sense in which units of flow travel from the source to the sink. From this more dynamic view of flows, we will arrive at something called the ST disjoint paths problem. The problem, in defining this problem precisely, we will deal with the two issues. First, we will make precise this intuitive correspondence between units of flow traveling along paths and the notion of flow we've studied so far. Second, we will extend the disjointed paths problems to undirected graphs. We will see that despite the fact that the maximum flow problem was defined for a directed graph, it can naturally to be used also to handle related problems on undirected graphs. We say that a set of paths is H disjoint if their H sets are disjoint, that is, no two paths share an H. Though multiple paths may go through some of the same nodes. Given a directed graph G equals to V with two distinguished nodes ST in V, the directed H disjoint paths problem is to find the maximum number of H disjoint ST paths in G. The undirected H disjoint paths problem is to find the maximum number of H disjoint ST paths in an undirected graph G. The related question of finding paths that are not only H disjoint but also node disjoint, of course, other than at nodes S and T, will be considered in the exercises to this chapter. Designing the algorithm. Both the directed and the undirected versions of the problem can be solved very naturally using flows. Let's start with the directed problem. Given the graph G equals to VE with its two distinguished nodes S and T, we define a flow network in which S and T are the source and sink respectively, and with a capacity of 1 on each edge. Now suppose there are kh disjoint ST paths. We can make each of these paths carry one unit of flow. We set the flow to be f of E equals to 1 for each edge E on any of the paths, and f of E prime equals to 0 on all other edges, and this defines a feasible flow of value k. 7.41. If there are kh disjointed paths in a directed graph G from S to T, then the value of the maximum ST flow in G is at least k. Suppose we could show the converse to 7.41 as well. If there is a flow of value k, then there exists the kh disjoint ST paths. Then we could simply compute a maximum ST flow in G and declare correctly this to be the maximum number of H disjoint ST paths. We now proceeded to prove this converse statement, confirming that this approach using flow indeed gives us the correct answer. Our analysis will also provide a way to extract the kh disjointed paths from an integer-valued flow sending k units from S to T. Thus, computing a maximum flow in G will not only give us the maximum number of H disjointed paths, but the paths as well. Analyzing the algorithm. Proving the converse direction of 7.41 is the heart of the analysis, since it will immediately establish the optimality of the flow-based algorithms to find the disjointed paths. To prove this, we will consider a flow of value at least k and construct the kh disjointed paths. By 7.14, we know that there is a maximum flow f with integer flow values. Since all h's have a capacity bound of 1, and the flow is integer valued, each h that carries flow under f has exactly 1 unit of flow on it. Thus, we could just need to show the following. 7.42. If f is a 0, 1 valued flow of value v, then the set of edges with the flow value f of E equals to 1 contains a set of VH disjoint paths. Proof. We prove this by induction on the number of edges in f that carry flow. If v equals to 0, there is nothing to prove. Otherwise, there must be an edge SU that carries 1 unit of flow. We now trace out the path of edges that must also carry flow. Since SU carries a unit of flow, it follows by conservation that there is some edge UV that carries 1 unit of flow, and then there must be an edge VW that carries 1 unit of flow. and so forth. If we continue in this way, one of two things will eventually happen. Either we will reach t or we will reach another v for the second time. If the first case happens, we find a path p from s to t, then we will use this path as one of our v paths. Let f prime be the flow obtained by decreasing the flow values on the edges along p to 0. This new flow f prime has value v minus 1, and it has fewer edges that carry flow. Applying the induction hypothesis for f prime, we got v minus 1 h disjoint paths, which, along with the path p, form the v paths claimed. If p reaches the node v for the second time, then we have a situation like the one pictured in figure 7.12. The edge in the figure all carry 1 unit of flow. And the dashed edge indicated the path traversed so far, which has just reached node v for the second time. In this case, we can make progress in a different way. Consider the cycle C of edges visited between the first and second appearances of V. We obtain a new flow f prime from F by decreasing the flow values on the edges along C to 0. This new flow f prime has value V, but it has fewer edges that carry flow. Applying the induction hypothesis for f prime, we get the VH disjoint paths as claimed. We can summarize 7.41 and 7.42 in the following result. 7.43. There are kh disjoint paths in a directed graph G from S to T if and only if the value of the maximum value of an ST flow in G is at least k. Notice also how the proof of 7.42 provides an actual procedure for constructing the k paths given an integer valued maximum flow in G. This procedure is sometimes referred to as the path decomposition of the flow, since it decomposes the flow into a constituent set of paths. Hence, we have shown that our flow-based algorithm finds the maximum number of H-disjointed ST paths, and also gives us a way to construct the actual paths. Bounding the running time. For this flow problem, C equals to the summations of CE summing for all E out of S, which is less than equals to the size of V, which is equals to N, as there are at most the size of V edges out of S, each of which has capacity 1. Thus, by using big O of M times C bound in 7.5, we get an integer maximum flow in big O of Mn time. The path decomposition procedure in the proof of 7.42, which produces the paths themselves, can also be made to run in big O of Mn time. To see this, note that the procedure with a little care can produce a single path from S to T using at most the constant work per H in the graph and hence in big O of M time. Since there can be at most n-1 H disjointed paths from S to T, each must use a different H out of S. It therefore takes time big O of Mn to produce all the paths. In summary, we have shown 7.44. The Ford-Fulkerson algorithm can be used to find a maximum set of H-disjoint ST paths in a directed graph G in big O of Mn time. A version of the max flow main cut theorem for disjoint paths. The maximum flow mean cut theorem 7.13 can be used to give the following characterization of the maximum number of H-disjoint ST paths. We say that a set F, which is subset equals to E, of edges separates S from T if, after removing the edges F from the graph G, no ST paths remain in the graph. 7.45. In every directed graph with nodes S and T, the maximum number of H-disjoint ST paths is equal to the minimum number of H whose removal separates S from T. Proof: if the removal of the set F, which is subset equals to E of H, separates S from T, then each ST path must use at least one H from F, and hence the number of H-disjointed ST paths is at most the size of F. To prove the other direction, we will use the max flow mean cut theorem 7.13. By 7.43, the maximum number of H-disjointed paths is the value V of the maximum flow, the maximum ST flow. Now 7.13 states that there is an ST cut AB with a capacity V. Let F be the set of edges that go from A to B. Each edge has capacity 1, so the size of F equals to V, and by the definition of an ST cut, removing these V edges from G separates S from T. This result then can be viewed as the natural special case of the max flow mean cut theorem, in which capacities are equal to R. In fact, this special case was proved by Menger in 1927, much before the full mean cut theorem was formulated and proved. For this reason, 7.45 is often called Menger's theorem. If we think about it, the proof of Hall's theorem, 7.40 for bipartite matchings, involves a reduction to a graph with a unit capacity agencies, and so it can be proved using Menger's theorem rather than the general max flow mean cut theorem. In other words, Hall's theorem is really a special case of Menger's theorem, which in turn is a special case of the max flow mean cut theorem. And the history follows this progression, since they were discovered in this order a few decades apart. Extensions, disjoint hypothesis in undirected graphs. Finally, we consider the disjoint hypothesis problems in an undirected graph G. Despite the fact that our graph G is now undirected, we can use the maximum flow algorithm to obtain the H disjoint hypothesis in G. The idea is quite simple. We replace each undirected edge uv in G by two directed edges uv and vu, and in this way create a directed version G prime of G. We may delete the edges into S and out of T, since they are not useful. Now we want to use the Ford-Fulkerson algorithm in the resulting directed graph. However, there is an important issue we need to deal with first. Notice that two paths P1 and P2 may be edge disjoint in the directed graph and yet share an edge in the undirected graph G. This happens if P1 uses directed edge UV while P2 uses edge VU. However, it is not hard to see that there always exists a maximum flow in any network that uses at most one out of each pair of oppositely directed edges. 7.46. In any flow network, there is a maximum flow F where for all opposite directed edges E equals to UV and E prime equals to VU, either F of E equals to 0 or F of E prime equals to 0. If the capacities of flow networks are integral, then there also is such an integral maximum flow. Proof. We consider any maximum flow F and we modify it to satisfy the claimed condition. Assume E equals to UV and E prime equals to VU are opposite directed edges, and F of E is not equal to 0, and F of E prime is not equal to 0 either. Let delta be the smaller of these values and modify F by decreasing the flow value on both E and E prime by delta. The resulting flow F prime is feasible, has the same value as F, and its value on one of E and E prime is 0. Now we can use the Ford-Fulkerson algorithm and the path decomposition procedure from 7.42 to obtain the H disjoint hypothesis in the undirected graph G. 7.47. There are kh disjoint hypotheses in an undirected graph G from S to T if and only if the maximum value of an ST flow in the directed version G prime of G is at least k. Furthermore, the Ford-Fulkerson algorithm can be used to find a maximum set of disjoint ST paths in an undirected graph G in big O of M and time. The undirected analog of 7.45 is also true. As in any ST cut, at most one of the two oppositely directed edges can cross from the S side to the T side of the cut. For if one crosses, then the other must go from the T side to the S side. 7.48. In every undirected graph with nodes S and T, the maximum number of H disjoint ST paths is equal to the minimum number of edges whose removal separates S from T.